Welcome back. Let's talk about relations and functions. And we're going to first start out with relations as a review of your previous work in algebra. What is a relation? Well, a relation is a set of pairs of inputs and output values. So a relation is a pair of input and output values. So a pair is going to be two things, right? It's going to be an input value and an output value. So a relation then can be represented in four different ways. So let's talk about the first way. The first way we can represent a relation are in what is called ordered pairs. And in an ordered pair, you have an input value and an output value. And they're inside parentheses with a comma in between. So, for example, -3, 4, 3, -1, 4, -1, and 4, 3. So the second way that we can represent these is through a mapping diagram. So a mapping diagram, same thing. We're going to represent an input value and an output value. So this side represents the input and this side represents the output. So using our numbers here, our input is 3, our output is 4. So that's paired with that one. 3 and -1. 3, -1. So we use the arrows to show how each pair works. Then we have 4 paired with -1. So it's paired with that -1 that's already there. So we don't rewrite -1. And then our last one is 4, 3. So that 4 is paired with that 3. So we can represent them in ordered pairs. We can represent them in a mapping diagram. And we can represent them in a table of values. And a table of values is going to take the same thing, right? An X, which is the input, and Y, which is the output. All right, so I've got my values here. I've got -3, 4 is my output for -3, 3, -1. I've got 4, -1, and then I've got 4, 3. All right, so I've got ordered pairs, mapping diagram, and table of values. And then the next way that I can represent those same ordered pairs is through a graph. So if I take my graph here and I create my X and my Y going up and down, and zeros at the origin, and I talk about -1 here, -2, -3, 1, 2, 3, 4, and I've got 1, 2, 3, 4, and -1, -2, -3, -4. All right, so I've got an input and an output. So I've got -3, +4. And I'm going to label that -3, 4. This is my first value, right? Then I've got 3, -1, which is right about here, and I'm going to label it. So I've got 2 points so far. And then I've got 4, -1, 4, -1, kind of right there in my way. So I'm going to put it here, and that's going to be 4, -1. It's kind of in the way, that's okay. And then my last value is 4, 3. So 4 and 3. 4, 3. All right? So a relation is a set of pairs of input and output values And what did I do? I represented them in ordered pairs, a mapping diagram, a table of values, and finally in a graph. Now let's just practice what we reiterated about the ways to represent those relations. We talked about that they can be represented with ordered pairs, a mapping diagram, a table of values, or a graph. Or all four of them, right? So here we have a skydiving example. When skydivers jump out of an airplane, they experience free fall. And the photos here show various heights of a skydiver at different times during the free fall, ignoring air resistance. Now the question is, how can we represent this relation in 4 different ways? So first we can represent this with a set of ordered pairs. So let's do that. All right, so I see over here 0 seconds. So my first one is 0 and 10,000. Don't confuse that comma there. All right. Next one is 4 seconds and 9,744. All right. Next one I have is 8 seconds at 8,976 feet. Next one I have is 12 seconds at 7,696 feet. And then we have 16 seconds at 5,904 feet. All right, so we represented them in ordered pairs. How else can we represent those? All right, we can represent them in a mapping diagram. All right, so mapping diagram. And in the mapping diagram, we have our input values on the left, arrow in between, and our output values on the right. So input, output, 0, 10,000, and I got an arrow going to it. 4 and 9,744, right? 8 and 8,976. Then I've got 12 and 7,696. Finally, I've got 16 at 5,904. None of those repeated, so I have each individual one with its own there. All right, so you can also represent this in a table of values. So our table of values has an input, right? We've got the input is time, and we're going to put the time in seconds, right? Because it says 0 seconds, 8 seconds, etc. And then our output is going to be height, the height. Okay, and we're going to say that height is in feet because that's what it tells us. So in 0 seconds, we're at 10,000 feet, right? In 4 seconds, we're at 9,744 feet. In 8 seconds, we're at 8,976 feet. At 12 seconds, we're at 7,696 feet. And at 16 seconds, we're at 5,904 feet. Okay, so we've represented them in the 3 different ways. And the last way that we can represent these is in a graph. So I'm going to grab my graph there so that we can see how those relate. Okay, I'm just going to put it right there on top of my mapping diagram. So what we have here is that we have a graph, and I'm going to get this stuff out of the way here just so we have our graph. All right, so in our graph, we have the pairs again represented at 0 feet. Remember, we had 10,000, so 0, 10,000, that's this one. Then we had 4 feet, 9,744, that's this one. Then we had 8 feet, which is going to be at 8,976. That's that one. Then we had at 12 feet, we have 7,696 is the height. And then finally at 16 feet, 16 seconds, we had 5,904, which is this one. So we have a graph of that height and the time that it's taking as we go. So we're represented actually by lots of things here, right? We represented by the table. We represented by the set of ordered pairs. We represented by the mapping diagram. We represented by the graph, table of values, and everything put together. And that's how we ended up with our representations for that, including our representation of the graph. Now, let's switch gears just a little bit and talk a little bit more about the next piece of our work today. We started out with relations. Now we're going to start talking a little bit more about functions. All right, so just a little bit of vocabulary here. We're going to talk about the word domain, and we're going to talk about the word range. Now, domain is of a relation is going to be the set of inputs. These are going to be our inputs. And then our range is the set of outputs. And they have values, right? So they have a value like we had a while ago. So the domain, for example, of this set of ordered pairs is 0, 4, 8, 12, 16. And the output, the set of the output is 10,000, 9,744, 8,976, etc. So domain are going to be all our input values, and then our range are going to be our output values. Now, domain, these are going to be in the sense of graphing. These are going to be our x coordinates. Those we go over on the x-axis, and the range values are going to be our y coordinates. And we can see that through the set of ordered pairs. So let's look at an example here, and we can determine from the relation what the domain and range values are. So I'm going to put these, I'm going to put our set of ordered pairs here that we had from previously. So we had 0, 10,000, remember? And we had 4 and then 9,744. Then we had 8 paired with 8,976. Then we had 12, I'm sorry. We had 12 that, and the height at 12 was 7,696. Finally, we had 16, and that height was 5,904. All right, notice these things first of all. When you use that notation, that denotes what's called a set. So inside that set is going to be a set of numbers that correspond to something. So if the domain, and I'm going to put domain, if the domain is the set of x coordinates, domain is the set of x coordinates, we're going to put it inside a set, and we're going to include those values. So the values are 0, 4, 8, 12, and 16. Those are my coordinates. All right, so 0, 4, 8, 8, 12, and 16. That's our domain values, and we use the set notation to indicate those numbers. Now, the range is the set of the y values. So our range is 10,000, 9,744, 8,976, 7,696, and 5,904. And my set closes. No, so this is not a set. That parentheses are going to denote a ordered pair, right? Like 0, comma, 10,000. But set denotes a set. So any relation is going to have a set of domain values and a set of range values. So because of that, let's talk about what a function is. So a function, we've been talking about relation up to now, but let's talk about function because that's the second half of what we're doing here. So a function is a relation, first of all, right? Is a relation. So what makes it different? So a function is a relation in which each element of the domain corresponds with exactly one range value. So corresponds with exactly one range value. Okay? So, let's look at this. We have a relation here. So let's identify this relation by using a mapping diagram. So on the left, we have the domain. On the right, we're going to have the range. All right. So on the left, I've got -3 paired with 2. And I use the arrow. I've got 0 paired with 7. And I've got it down here. And then I've got 4 paired with 1. So is this relation a function? Is it a function? A relation is a function if each element of the domain corresponds with exactly 1. So that -3 is paired with 2. That 0 is paired with 7. That 4 is paired with 1. So yes, this is a function because each element of the domain corresponds with exactly one element in the range. Well, let's look at another one then. If I have a set here, and I've got 4, -1, I've got 8, 6, I've got 1, -1, and then I've got 4, 1. All right, so I've got 4 is paired with -1. I've got 8 is paired with 6. I've got 1 is paired with -1. Okay, I've got a problem here. So while this is a relation, the definition of a function says that each element of the domain corresponds with exactly one range value. Here, both 4 and 1 correspond with -1. So the relation then is not a function. So you can look at any relation and look to see to make sure that each value corresponds, each domain value corresponds with only one value there in the y value. And if it does, then it's going to be a function. Let's look at another way to determine a function on a graph. Okay, so another way to look at a function and at a relation and determine whether that relation is a function is to use what is called the vertical line test. I'm going to call it the vertical line test. Now, a vertical line goes up and down. That's a vertical line. The other one is a horizontal line. Now, the vertical line test says that if a vertical line passes through more than one point on the graph of a relation, then that relation is not a function. So, let's pass my vertical line through the very first set here, that very first graph. So I've got a graph, and lo and behold, my vertical line, my ruler, keeps hitting 2 points right here. See that? It hit that point, and it hit that point. So that first graph is not a function. What about the next one? Let's see. Good, 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 good. My vertical line did not hit 2 points on the graph, right? So B then is a graph of a function. Now, what about our last one? C. All right, so see how those points are there? Okay. All right, good so far. But lo and behold, we hit 2 points right here and right there. So that third graph, graph C, is not a function. So you can use a vertical line test or actually just kind of see it, right? But the vertical line is a really good way to do this. So we've looked at some ways to determine whether a relation is a function. And we looked at it through the mapping diagram, then we looked at it with the ordered pairs, and then if it's already graphed, we can use the vertical line test. All right, we now know how to determine whether a relation is a function. So let's talk a little bit about using function notations, and we're going to start out with what we call the function rule in an equation. So the function rule is an equation. And in this equation, that equation will represent an output value in terms of an input value. So it is an equation that represents an output value in terms of an input value. Now, you can write what is called a function rule in what we call function notation. And we're going to use function notation to look at if we have an equation that is a function, then we're going to use function notation. So let's look at a function rule first by starting with an output-input equation. So if I have this equation, y equal 3x plus 2, that y is my output. That's what happens when a value is multiplied by 3 and then we add 2 to it, right? So this is my input. So whatever happens here, the output is going to be my y value. So in function notation, that same one looks like this. F of x equal 3x plus 2. So this right here, it's not any different than that other than it is now in what we call function notation. And we read this, f of x, or function of x, equal 3x plus 2. Now, another way to use function notation when we're going to substitute 1, for example, into the x value, we can say f of 1 equal 3 times 1 plus 2. So if we were substituting 2 in for the x value, we would say f of 2 equals 3 times 2 plus 2. So f of 2, if I evaluate that, that's 6. 6 plus 2 is 8. So f of 2 is 8. So we have a couple of things here in our function notation. We have an independent variable, x. right? That represents the input of the function. And then the dependent variable, f of x, represents the output. So that's our output. We have an independent variable x. We have a dependent variable, which is our f of x. It's called the dependent variable because its value depends on the input value. Now then, let's use function notation. So let's look at it this way. If we have our function notation, we want to know what the output is when we have three different inputs. All right? So let's look at it. We've got f of x equal negative 2x plus 5. So we want to know what is the output when we have negative 3 as the input, 0 as the input, and 1/4. So we want to know what those outputs are. So we're going to set it up like this. X is our input. We have the function rule here. And I'm going to write it down here. We've got f of x equal negative 2x plus 5. And then over here we have our f of x, which is our output. All right, so start with our first input here, which is negative 3. So let's use function notation. F of negative 3 equal negative 2 times negative 3 plus 5. So negative 2 times negative 3 is positive 6 plus 5. So our output is 11. All right? Next input value is 0. So f of 0 equal negative 2 times 0 plus 5. Negative 2 times 0 is 0 plus 5. So my output is, you guessed it, 5. All right? Now I have one more. I've got 1/4. So now we can say f of 1/4 equal negative 2 times 1/4 plus 5. So we've got negative 2 times 1/4, that's negative 2/4 plus 5, or negative 2 and 1/4 plus 5. So when I reduce this, I get negative 1/2. So I have plus 5, I have negative 4 and 1/2. So you can go over to the side and add those if you need to. So I've got my function notation, and we figured out what the output was when we were given 3 inputs. So we can do that in any way when we're given an input. All right, now let's write and then evaluate a function using this story problem here. So let's go through this together. Tickets to a concert are available online for $35 each, plus a handling fee of $2.50. The total cost is a function of the number of tickets bought. What function rule is going to model the cost of the concert tickets? So first we got to do that. And then it says evaluate the function for 4 tickets. All right. So let's kind of break this down and start thinking about the dependent variable here. So the cost is going to be the dependent quantity and the number of tickets is independent. So cost is going to be the dependent, right? And we said that the number of tickets is going to be the independent quantity. So let's look at this. So the total cost, I'm going to look at it like this, is the cost per ticket. I'm just putting this in words, right? Times the number of tickets bought and this will make sense as we go through this, plus the handling fee. So we have that handling fee that is constant, right? It's going to be $2.50. So now let's define those that we just talked about. So we're going to define that. So our definition is we're going to say T, we're going to use T as the number of tickets bought, equal number of tickets bought, right? All right, and then C of T, our cost, right, is going to be our total cost. Notice that C of T is in function notation, right? So now let's write this out. We've got C of T equal, we said $35 each, right? 35 T, which is $35 for each ticket, plus our handling fee, which is $2.50. Now, we wrote our function here. Now we want to know and evaluate that function for 4 tickets. So we're going to say C of 4, or the cost of 4, equal 35 times 4 plus $2.50. 35 times 4, I'm going to go over here, 35 times 4, 5 times 4 is 20, that's 140, plus $2.50. 140 plus $2.50. That gets me $142.50. So C of 4 equal $142.50. So for 4 tickets, the cost, so after I do the math, I need to answer the question. The cost of 4 tickets is $142.50. All right, so we wrote a function and we evaluated that function for 4 tickets. Now that you have a function, you can evaluate that function for any number of tickets. You have an input value, that's going to be how many tickets you want, and then your output value is going to be the cost.